So let me start where we were last time. Okay, so we had seen linear transformations. Between two vector spaces. So these were usually denoted T from V to W, right? And these were these natural transformations which preserved the vector space structure, right? So in particular, preserved addition, preserved scalar multiplication. Okay, and then we saw some examples of this. So let me give, just write down again the example that we kind of ended with last time, I think. So we had this transformation from R2 to R2, which was a linear transformation. I mean, at this point you can assume for the rest of the course, I think, that every function between vector spaces that I write is going to be a linear transformation. And then what we did was, well, we had a basis, E1, E2 for R2, just the standard basis. So then any vector in the domain was alpha 1 E1 plus alpha 2 E2. We knew that T of V was alpha 1 T of E1 plus alpha 2 T of E2, and this let us conclude that if we knew what, where the first basis vector went under T, and we knew the image of the second basis vector under T, then we would know what the image was for any other vector, right? So if we know, maybe I'll change this. So if we know VI, which is just T of EI, then we know T of V for all V and V. Okay? And what this lets us do is encode, so this fact lets us encode T in a matrix. So I will, say what a matrix is just in a second. Essentially, it's going to be, it's a array of numbers, and the way that we write down the matrix is you let the columns of the numbers be the images of the basis vectors. Okay? So I'm going to say what a matrix is first off, and then I will say exactly how you get this matrix and how you multiply vectors by matrices to get you these linear combinations, or to get you these transformations. Okay, so what is a matrix, for those that haven't seen this? So it is an array of, it's an array of numbers. Usually, I'm going to denote this by mn, okay? And what this means are these are the m by n matrices. Oh, I should say, sorry, so the numbers, well, it depends on what the field are that you're interested in. So usually, by numbers, I just mean elements of some field. Okay, but I'm usually thinking of R or C, okay? So when I denote this, we're looking at m by n matrices, so these are arrays of elements in this field with m rows and n columns. Okay, so I'll write some examples first. And then usually I denote A some ij to be the element in the ith row and the jth column. Okay, so let me give you an example. or some examples. Maybe I'll do, I don't know, 1, 2, 3, 4, 5, 6. Okay. So this has 2 rows and 3 columns. So this is a 2 by 3 matrix. And then you should just, of course, the largest mistake that you ever make, or the kind of the only mistake that you ever make, is that you forget row versus column and column versus row. It's never anything huge, but of course you don't want to get it wrong. Okay, so maybe I'll just put this here, like for example, A1, 3, for example, is the first row and the third column, so this is just 3. Okay, A2, 2 is 5. Okay, and when I say that it's the only mistake you can make, I guess I mean to say I will be making this mistake probably a lot, and you have to be careful to catch me. Okay, so anyways, so this is how you get the entries of this matrix. In general, this is how these look like. So maybe an important case is when m is n. So I don't know, here's a good matrix. This is a 3 by 3 matrix. In general, when you have the same number of rows and columns, we call this a square matrix. Okay. Let's see. So that's, maybe I'll say one more thing about these. So they themselves are a vector space over, whatever field the elements in the matrix come from. Okay, so I'll leave this for you as an exercise to check. So, what you should think about, so maybe I should tell you the operations, that would be a good thing to do. So the operations are, well, there's an obvious way to add matrices together. You just add component-wise, right? So, you should also think, which matrices you can add together. So, 1, 2, 3, 4, 5, 6 plus 4, 5, 6, 1, 2, 3 is just the matrix 7, 9, 5, 7, 9. If I did that right. Okay. So of course, when I'm saying that it's a vector space, you have to look at the n is a vector space. There's not a natural way to add, an mn matrix to a pq matrix. And then scalar multiplication. Well, again, I can just take something like a scalar multiple, and I just do it component-wise again. So I just multiply every entry by that scalar. Okay? And you can check that this kind of obviously satisfies the axioms of a vector space. So this would be like 2, 4, 6, 8, 10, 12. Okay? So how do we encode this transformation as a matrix? Well, I said kind of how to do it using these column vectors. So let me maybe make it more explicit here. So I said we had this matrix from R2 to R2, where I said, and then we had T of E1 and T of E2, okay? And now notice, well, we also have a basis for R2, right? we have a basis for the domain. So here, since it's the same vector space, I can make it the same basis, okay? So I can write each of these, the images of my basis vectors, in terms of the basis of my range. Okay, so in particular, T of E1 is some scalar times E1, so I'm going to write this as alpha 1, 1. Okay, I will probably leave out the comma at some point. E1 plus alpha 2, 1, E2. Okay? T of E2, again, these are just scalars that, depend on whatever these images are. And the labeling is just, at this point, I'm just doing it conveniently. Okay, is alpha 1, 2, E1 plus alpha 2, 2, E2. Okay, so the point is that I naturally, from this linear transformation, I produce 4 numbers, right? The way that I do that is I take a basis for my domain, I look at its image, and then I write the image of each basis vector as a basis vector in the range, okay? Or it's a linear combination of basis vectors in the range. So I get 4 numbers, and these are encoded in the matrix where I just write 1, 1, alpha 2, 1. Okay, so this is my T of E1, and then I get alpha 1, 2, alpha 2, 2. Okay, so this is the matrix encoding T. Okay, so now we have some sort of representation of the linear transformation. Of course, it's also convenient to be able to kind of work with these matrices. So we kind of, we can just compute using a matrix what this linear transformation does, right? That will be convenient for us to do. Okay, so what we want is a way to multiply a vector by a matrix so that when I take like T of V, it's the same as multiplying by some, okay, so I have to call this matrix something. Maybe I'm just going to call this A, okay, is AV, okay? So the first kind of useful thing to do is encode or represent V as alpha 1, alpha 2, okay, where V is, again, I'm just thinking about the standard basis, alpha 1, E1 plus alpha 2, E2, okay? So this, is an alternative way to describe whatever V is. It's just using whatever the coordinates are in this particular basis. So maybe I should just emphasize, I'll say this later, but of course this all depends on the basis, right? If I had a different basis, then you would get a far different, matrix. Okay, or I could have chosen one basis for E1, E2 for R2 and chosen a completely different basis for the range R2. Again, that will change the basis or change the matrix. So in some sense, the matrix is not as nice a thing or as natural a thing to work with as linear transformation, but it's also a very useful way to compute things, so have to take what you can get. Okay, so anyways, what we would like is a way to represent alpha 1, 1, alpha 1, 2, alpha 2, 1, 2, and I've realized that I'm going to have too many alphas here, so let me just change these to betas, okay? So I have beta 1, beta 2, okay? Okay, so now what we know is that, well, T of V is beta 1 T of alpha 1 plus beta 2 T of alpha 2, okay? And here, this is the numbers that I've encoded, T of E1 and T of E2. Sorry, I think I said alpha, okay? So the way that you get a new vector from this is, well, you multiply beta 1 times alpha E1 and multiply beta 2 times the second column. So the way that you write this is beta 1 times alpha 1, 1, alpha 2, 1 plus beta 2 alpha 1 2 times alpha 2 2. Okay, so notice I'm kind of using the fact that the matrices are a vector space, right? So I'm allowed to multiply these columns, which I'm thinking of as just, 2 by 1 matrices. I can add them and I can multiply them by scalars. Okay, so let me give you an example of this, and then I'll do another way. This is slightly different that perhaps you've seen, but I mean it's turns out to be equivalent to maybe the usual way to multiply matrices. Okay, so let me do an example. So I don't know, let me just pick 1, 2, 4, 7. I don't know, sounds like a good example. And let's see where it sends the vector 2, 3. Okay? So what I do here is I take 2 times the column 1, 2 plus 3 times the column 4, 7. So I get 2, 4 plus 12, 21. So I get 14, 25. Okay? So this is just saying that the linear transformation that sends 1, 0 to 1, 2 and 0, 1 to 4, 7 sends 2, 3 to 14, 25. Okay, so maybe another kind of sanity check is that when I plug in E1, which in this case is given by 1, 0, then I get precisely 1 plus the first column plus 0 times the second, so I just get 1, 2. Similarly, if I take 1, 2, 4, 7 times 0, 1, I get 4, 7. Okay? So it sends, this is E1, this is E2, and the formula is correct in the sense that it produces those images. Okay? So maybe I'll just give the other way that people usually compute using matrix multiplication with the same example. It's doing what I did, but in kind of maybe a couple fewer steps. So what people say is, well, what you do is you take 1 times 2 plus 3 times 4. Okay, so you look at this row and you multiply it by this column by multiplying the first 2 coordinates, multiplying the second 2 coordinates, and adding them together. Do the same thing here, so you get 2 times 2 plus 3 times 7, but of course we can check that this, is equal to 14, and that's equal to 25. It's exactly the same procedure, just written slightly differently. Okay? So maybe I'll do the kind of the general formulation now. Okay? It's going to be very similar. So, here, general case. So what do I mean by general case? Well, at this point, I'm just going to be thinking about linear transformations from Rn to Rm. Okay? Then what I get is I have n basis vectors, which again I'm going to think of as standard basis vectors, E1, in the image. These are going to be my columns. I can write the image of each one of each basis vector in terms of maybe I'll call it the f sub I, which are just, again, the standard basis vectors, but now there's n of them. Okay, so there's m, so I equals 1 to n, I equals 1 to m. So you write these in terms of this basis vector, so in other words, you get a linear combination in terms of the f sub i's, then the matrix that you write is an m, let's see, so there's m rows and n columns, and you write each image in the column. Okay, so you have t e1 up through t of en. Each of these, so the number of terms in each column is m, and there are n of them. Okay. And to be precise, the way that I get the ijth entry in this matrix, so it's the ith row, jth column, is by finding t of ej, okay, and then writing it out as alpha 1 f1 plus, I'll write it here, alpha I fi up to alpha m fm, and then I take alpha I. Okay. So in other words, when you write the jth basis vector in terms of the image of it in terms of the other basis, it's the scalar in front of the ith basis vector in the range basis. Okay, so let me just make this note, which I made before, but I just want to make it explicit, right? So if I have a t from v to w, which is a linear transformation, and bases for v and w, I get a matrix encoding t. And then, of course, if I'm choosing different bases, produces different matrices, okay? And you can, a good, decent chunk of this class will be, in some sense, finding the correct basis, okay? So what we would like a basis, or two bases, where the transformation matrix is as easy to work with as possible. Okay? So of course, it depends on what the transformation is. But what would be nice is if you could choose bases where the matrix encoding the transformation is a very easy form, right? Then it's easy to compute with, and you can try to get a good geometric understanding of what this transformation is actually doing. Okay, so let me give you some examples, all right? Let's put that there. Okay, so examples. This will go again from R2 to R2. So let's send t, which goes to x, and y goes to x plus y. I'm just going to do this from R2 to R2. You can do the same thing for other fields. Okay, so this is an interesting enough linear transformation that I'd like to have a picture of it. Okay. So here's an idea of what this does. It's called like a shearing map. So notice that if I look at the points 0, x, then, well, this goes under t to 0x. Right, or sorry, I guess I'll make it y, not to be too confusing. Okay, so if I look at 0y, which is a point on the y-axis, then when I do this transformation, I can just get 0y again. Okay, so this is fixed under t. And let's see what happens to I don't know, 1y. Okay, so 1 is fixed and y can be anything. Well, of course, this goes under this to 1y plus 1. So here, on the x equals 1 coordinate, or this line, we have translation by 2. Okay. On the 2y coordinate, we have this goes up to 2, and to 3, and so on. Okay, so what you end up with is this picture where, and this is why it's called a shear. You have translation upwards, right? So if you fix a vertical line, then this transformation just acts by translating up on that line. But on the other hand, it depends how far you push up depends on how far away you are from the y-axis. Similarly here, if you're in the negative coordinates, then you push farther and farther, depending on how far away you are from the y-axis in the negative direction, but now you're pushing negatively. Okay? So that's like what this transformation is doing. It's shearing things upward or downward, depending on whether you're negative or positive. Okay? And the matrix for this, well, we just see where the E1 and E2 go. So where does 1, 0 go to? Well, it goes to 1, 1. I get 1, 1. And then where does 0, 1 go to? It goes to 0, 1. Okay, so that's the matrix for this transformation. Okay, so let me do another example. Another useful one to know is I'm going to take the matrix. So I won't even, we kind of know what it does now. So I'll write 2, 1, 1, 1. Okay, so this sends E1 to 2E1 plus E2, and it sends E2 to E1 plus E2. All right, so let me, again, try to draw a picture here. I'll just draw an image of where the basis vector goes. So here's kind of a rectangle spanned by E1 and E2, and then this goes to the parallelogram. So let's see, so E1, 2E1 plus E2, 2E1. Okay, something like this. So this is T of E1, and this is T of E2. Okay, so this is a perfectly good basis. We have this linear transformation. It gives you some idea of what this linear transformation is doing. Okay. But here's something to check. Okay, I'm gonna kind of pull this from a hat. But if you do the computation, you'll notice that if you apply 2, 1, 1, 1 to the matrix 1 plus square root of 5, 2. Well, okay, I guess I can do this out for you. So this is 2 plus 2 square roots of 5 plus 2, and then 1 plus square root of 5 plus 2. So we get 4 plus 2 square roots of 5, and then 3 plus square roots of 5. Okay, so that seems sufficiently random at this point. Okay? But now notice that these matrices, or these vectors, are actually related, right? So if I take 1 plus square root of 5, 2, and I multiply it by just a scalar now, by the scalar 3 plus square root of 5 over 2, again, this will seem pulled out of a hat, and that is okay, okay? I can be a magician at some points. Then you can check just by multiplying the scalars, right, that you get exactly 4 plus 2 square roots of 5, 3 plus square root of 5. So in other words, the vector 1 plus square root of 5, 2. Okay, so I'm going to, again, I denote it this way. Of course, this is just xy coordinates in R2, right? So it's 1 plus square root of 5, 2. Okay, so this vector goes to a scalar multiple of itself. So if I draw the picture here, so 1 plus square root of 5, 2, I don't know, it will, all my dimensions or pictures are going to be slightly off. But this goes to a scalar multiple of itself where you multiply by 3 square roots of 5 over 2. So it goes to something where that's supposed to be on the exact same line through the origin, but just multiplied by this value. Okay? You can also check that the same thing happens that the same behavior happens for the vector 1 minus square root of 5, 2. Okay? Again, if you check, if you see where this goes under t, it goes to 3 minus square root of 5 over 2 times itself. Okay? So in other words, if I look at these two vectors, I get t of v1 is alpha 1 v1, and t of v2 is alpha 2 v2. So maybe I can try to draw the picture here. So 1 minus square root of 5, 2 is somewhere pointing over here. Wrong direction. Should be like pointing more up here. Okay? And it's multiplied by something which actually shrinks it. Okay, so it goes to, again, it's a scalar multiple of itself, but it shrinks. So you kind of get this expansion in this degree and contraction here. Okay? But now, well, the point is, so now, you can see that v1 and v2 form a basis for R2. Okay? I'm not going to prove that. It's something to check, but you have two vectors, right? So you only have to check that you can write everything in a unique way in terms of this vector and this vector. It turns out not to be too hard a computation. Okay? I would say, okay, check this. So now, when you write it out in this basis, so the matrix, where I choose the same basis with the basis, v1, v2, chosen for both the domain R2 and the range R2, has this form. Right? You just you take the first one, it goes to a multiple of itself, and nothing in the second coordinate, right? So this would be like, this is secretly plus 0 v2, and this is 0 v1. Similarly, this is 0, 3 minus square root of 5 over 2. Okay? So we have two completely, maybe I can pull this up. We have two completely different matrices defining the same linear transformation. But now, you kind of have to check which one, if you want to really understand the geometry of this linear transformation, well, you have some options, right? And one is not necessarily better than the other. They're telling you different things at different points, right? So maybe you like this picture of knowing that this rectangle goes to this parallelogram, okay? That's one good thing to know. Or maybe you like the fact knowing that you have this, expansion in this direction and contraction in this direction, okay? So we'll see, this will come up periodically throughout the course. It's going to be a major focus of it, but I just wanted to give you this example now of explicit matrices that represent the same transformation. Okay, so finally, maybe I'll make one more small remark here, which may or may not come up later in the class, but it's a nice thing to note, okay? So notice that, I'll just stick with this map. So the transformation 2, 1, 1, 1 preserves, just gonna leave that, preserves the elements of R2 of the form AB in the integers, okay, as a set. Okay, so maybe I'll draw the picture here. All that I'm saying in this case is that, well, all the elements of my matrix are in the integers, right? So therefore, if I take any, point here, which looks like AB, where A and B are in Z, so I don't know, I drew the point 4, 1. Well, this goes to the point 2A plus B, A plus B, right? And therefore these are also in the integers, okay? So this turns out to be another important way to think about a matrix, or to think about the linear transformation, that it induces. Somehow there's some arithmetic which is preserved, because anytime I have a point which is on this, what's called the integer lattice, it goes to another point in the integer lattice, okay? This is kind of difficult to see when you write things with respect to this basis, right? With respect to v1, v2, but again, it's something that is independent of the choice of basis. So this linear transformation does preserve this lattice no matter what basis you choose. It's just, this makes it quite obvious, and this is a mess. Okay, so let me do some more examples, which will come up. So we had seen before that rotations are linear transformations. So we should see what they are as a matrix, right, with respect to the standard basis. Okay. So in this case, so I guess I'll rotate counterclockwise, alpha radians. Okay. Well, so then where does 1, 0 go? Or I'm going to write this in the standard basis. So, and I'll write it as a column matrix now. I'm going to try to get in that habit. So 1, 0 goes to, it goes to the point on the unit circle of rotated alpha round, which is the x-coordinate, since we're on the unit circle, is cosine alpha, and the y-coordinate is sine alpha. On the other hand, the second basis vector goes to, it's cosine of alpha plus pi over 2, sine of alpha plus pi over 2, which people write as negative sine of alpha, cosine of alpha. So in other words, we get for the matrix, these go to the columns, so we get cosine alpha, sine alpha, negative sine alpha cosine alpha. And if I plug in a random point on in R2, then this goes to x cosine alpha minus x sine alpha, y sine alpha. Sorry. Y sine alpha x sine alpha minus y cosine alpha. Okay, so let me do some more geometrically interesting ones. Or not more of the same geometrically interesting ones. So we had seen before reflections. And this will, well, so I can do some reflections, right? So we've seen reflecting over the x-axis, for example, is a linear transformation. And this ends 1, 0 to 1, 0, 0, 1 to 0, minus 1. So we get the matrix 1, 0, 0, minus 1. So this is a perfectly good linear transformation. For other reflections, so if I just pick a random point, y is mx, notice again I have to reflect over the origin for this to make sense, or if I want to write down a linear transformation. If I want to write down this one, this immediately becomes more of a hassle, right? So, you know, in general, it's difficult to say, well, where does 1, 0 go if I want to write down the matrix for this reflection. So what we'll see is we had before that the way that you could, so reflecting over y equals mx, is a composition, which I'll write it as, so of rotating and reflecting over the x-axis. Okay, so this will motivate what we're going to do at the start of the next video, which is to work out in the language of matrices what composition translates to. Okay, so composition goes to something. Okay, it will turn out to just go to, if you've heard matrix multiplication, this is precisely the analog of it, or the translation of composition to this language. So we'll see that next time. So maybe I'll just mention here that kind of obviously a composition of two linear transformations is a linear transformation. Okay, so maybe I'll just write this down. So if I have t from v to w in general, and t prime from w to u, then I can look at t prime composed with t, which goes from v to u. Okay, I want to show that this is a linear transformation. Maybe I'll just sketch the argument. I mean, it's very straightforward. So I take v. What I need to show is if I take alpha 1 v1 up to alpha n vn, that this is some linear transformation or linear combination of elements of u. Okay, so this should go to a linear combination. And, well, we know t sends it to a linear combination, so t prime of t of this is t prime of alpha 1 t of v1 plus alpha 2, all the way up to alpha n t of vn. And then I do the same exact thing, since this is a linear transformation. This is a linear combination of elements of W. I get this is alpha 1 T prime of T of V1 plus all the way up to alpha N T prime T of Vn, which is a linear combination in U. Okay? So it is linear. On the other hand, writing down a matrix for this for this linear transformation gets a little complicated, right? We have to plug this in for a matrix, then write it down as basis elements for something in W, and then apply T prime, which lets us choose something in U. So we'll see that there's you can write down exactly what it has to be, and there's a nice way to encode this all in terms of matrices. Okay, so I'm just going to give one more example, which is, I'll give two more examples. One of them is, again, both of them are important. But now I'm thinking of geometric constructions in Rn. So the other kind of natural transformation you can do is projections. Okay, so I'll just give you a specific example. Maybe let's first start with projection onto the x-axis. Okay. So I can send any point xy to x0. Okay. Just writing it out in column vectors. Okay, so in particular, you can check. So for one thing, you have to be a little, you might say, well, I could have just sent this from R2 to R, right? Send xy to x. There are reasons why you actually want to think of this as a subspace of R2. In particular, if you want to start composing these things, it's helpful to keep the same range as domain. Either way, you'll get a different matrix if you write out this way. Maybe I'll leave this as an exercise to think about what a matrix could be, okay, if you were going to R. In this case, in this standard basis, 1, 0 goes to 1, 0, and 0, 1 just goes to the 0 vector. Okay, so this is the matrix in this standard basis. Okay, so this is x0. If I want to do another projection, say onto, so notice it's not going to be a linear transformation unless I project onto an element, or a line, in this case, which passes through the origin. Okay, so this is like a line y is mx. Then what I do here is if I want to figure out what this, the matrix in the standard basis is, well, I can again write this as a composition. So projecting to this line is the same thing as rotating the line to the x-axis, which we know the matrix for. Then project, and then rotate back. Okay, so I'll just do the line y equals x, for example. In this case, you can figure out exactly what has to happen here, or where the points go. So 1, 0 and 0, 1 both get sent to the line, or to the point 1, 1/2, 1/2. Okay, so 1, 0 and 0, 1 go to 1/2, 1/2. So the matrix is just a matrix of all halves. And it's also kind of easy to see geometrically that what you're doing here, when you project to the diagonal, is exactly of xy, is exactly sending this point to the midpoints of your x-coordinates and your y-coordinates. Okay. So this has a nice, it's an orthogonal projection in the sense that if I follow this line that I'm projecting along, it hits the diagonal at a right angle. We'll see these are important things to consider later. But I think for today, that's all I had. So thanks.